Four complex numbers z1, z2, z3 and z4 are shown on the Argand diagram. They satisfy the following conditions. z2 is I times z1, z3 is k times z1 where k is a real number, z4 equals z2 plus z3. The same scale is used on both axes. Identify which number is which by labeling the points on the diagram. Let's start by looking at this relation here first of all. So one of these complex numbers is the sum of two of the other three complex numbers. So what does the sum of two complex numbers look like? Suppose we want to get the sum of these two numbers, 2 plus 4i and 3 plus 1i. Well, we know how to do that. We add the real parts together. 2 plus 3 is 5. And then we add the imaginary parts. 4 plus 1 is 5. So we get the complex number 5 plus 5i. So we go out 5 and up 5. And here it is, 5 plus 5i. Now, how could we sum these two complex numbers geometrically? Well, we could look at the lines joining each of these points to the origin and complete a parallelogram. So here is the picture. If you know anything about vectors, we could think of the complex number 2 plus 4i as a vector whose tail is at the origin and whose head is at the point with coordinates 2, 4. Similarly, we could think of 3 plus I as a vector whose tail is at the origin and whose head is at the point with coordinates 3, 1. This point is coordinates 3, 1. This is coordinates 2, 4. And to get the sum of these two vectors, which is this vector here, we just complete a parallelogram. We draw a line parallel to this line, and we draw another line here parallel to this line, and we draw in the diagonal of the parallelogram. And that diagonal is called the resultant of these two vectors, or the sum of these two vectors. So that's the connection with vectors, the connection between complex numbers and vectors, or coordinate geometry and vectors. So, anyway, if you haven't seen vectors, it doesn't matter. Just keep in mind this diagram. So we're summing two complex numbers. So just imagine drawing a line from the origin to each complex number, then completing a parallelogram and drawing in the diagonal of the parallelogram. And this point here is the sum of the two complex numbers. Now if we go back to this situation here, we have four complex numbers shown. One of them is the sum of two of the other three. So it's not too difficult to see that this complex number here is actually the sum of this one and this one. So if we take these two and add them together, we will get this one. In order to add this complex number onto this complex number, we have to complete a parallelogram. So we have to draw a line through this one, parallel to this side. And draw a line through this point, parallel to this side here. Then we draw in the diagonal. So this, if you want to go back to thinking in terms of vectors, this vector added onto this vector gives us this vector. Or this complex number added to this complex number will give us this complex number here. So basically this complex number must be Z4. This is the only complex number which can be got by adding two of the other complex numbers. You can check for yourself that you cannot get this complex number by adding two of these three, or you cannot get this one here by adding two of these three, or you can't get this one by adding two of these. You won't be able to form a parallelogram. You can only form a parallelogram by adding this complex number onto this complex number and getting Z4. Z4 is at the corner of the parallelogram made from these two complex numbers. So either this one is Z2 or this one is Z3. So this could be Z2 and this one could be Z3, or vice versa, because the order of addition doesn't matter when we add complex numbers or when we add vectors. This could be Z2 and this could be Z3. So we need more information to decide which of them is Z2 or Z3. Actually, if we look at this relation here, we see that Z3 is a scalar multiple of Z1. So K is just a real number. If we multiply a complex number by a real number, we get a complex number that's on the same line as the original complex number and the origin. For example, if we multiply 3 plus I by 2, we get the point with coordinates 6 plus 2i, this point here. 6 plus 2i is on the same line as 3 plus 1i. So to get 6 plus 2i, I multiplied 3 plus 2i by a real number and multiplied it by 2. So if you multiply a complex number by a real number, all you do is stretch the complex number, if you like. It's still lying on the same line, but we in this case, if we multiply by 2, we've doubled the modulus of the complex number. It's the same idea in vectors. We take a vector and multiply it by a scalar. Say in this case the scalar is 2. Then we scale up the vector 3 plus I by a factor of 2. If we multiply 3 plus I by a half, we would get this complex number here, or this vector, if we're talking about vectors. So we could scale it up or scale it down. If we multiply a complex number by a negative number, we would get a complex number out here. But again, if we join the complex number to the origin, everything lies on the same line. So multiplying z1 by a real number k will not rotate the complex number. So we need a number that's on the same line as z3, and obviously it's this one here. So this number is actually z1, because if we multiply a scalar by z1, we get z3. z1 and z3 and the origin are on the same line. So that means that z1 is a scalar multiple of z3, or we could say z3 is a scalar multiple of z1. So it's important that we call this point z3. We could have called it z2 because we know that z2 plus z3 gives z4, but this one must be z3 because z3 is a scalar multiple of the remaining complex number z1. So we can't have z2 here. If this is z3, then its scalar multiple would have to be on this line, and there is no other number on this line. z1 is on the same line as z3 and the origin, so z1 must be a scalar multiple of z3. As a matter of fact, you can see that k must be a number less than 1 here. It's actually, it looks like it's about a half. If we get half of z1, we get z3. If we half the modulus of z1, half the distance of z1 to the origin, it gives us the distance of z3 to the origin. So it looks like k is equal to a half. And that's a question we have to answer in part 2. So I'll just do that now. Just while we've come across it, just write it in. K must be a half. We can see that z3 is half of z1. So like this example here, if we were to get half of 6 plus 2i, we would get 3 plus 1i. So now we have identified all 4 complex numbers. What about the last relation? So by default, this relation must be true because we've identified everything. So let's just confirm that it is true. z2 equals I times z1. What effect does multiplying I by z1 have on z1? Well, let's take an example. Let's look at the complex number 3 plus I, and let's multiply it by I times 3 plus I. See what the effect of multiplying a complex number by I is. I've covered this in a previous video. But anyway, we get 3i plus I squared. I squared is minus 1. We write the real part first. The real part is minus 1. The imaginary part is plus 3i. So we get the complex number minus 1 plus 3i, which is here. So multiplying 3 plus I by I has the effect of moving it to here. I'll just connect minus 1 plus 3i to the origin. Actually, it has the effect of rotating the complex number about the origin through an angle of 90 degrees. More precisely, the complex number is rotated anti-clockwise about the origin, going in the anti-clockwise direction through an angle of 90 degrees. And the distance of 3 plus I to the origin is the same as the distance of minus 1 plus 3i to the origin. So the modulus of both of these complex numbers is the same. And that's very easy to see. We can get that from Pythagoras. You can see from the diagram, we have a right angle triangle, base 3, height 1 This one here is height 3, base 1, so the distance of 3 plus I to the origin is root 3 squared plus 1 squared. We just square the real and imaginary parts and sum, so that gives us root 10. So that distance there is root 10, and this distance here is also root 10. So the modulus of both complex numbers is the same. So if we go back to this diagram, we're multiplying I by Z1. So that will have the effect of rotating Z1 anti-clockwise through an angle of 90 degrees about the origin. So if we just connect Z1 to the origin, and if we imagine rotating this line 90 degrees anti-clockwise about the origin, it looks like we get Z2. Z1 ends up at Z2, and the distance of Z1 to the origin looks to be the same as the distance of Z2 to the origin. So everything makes sense. We didn't really have to look at this relation, but I just want to, just for the sake of completion, just explain that everything makes sense. Indeed, we could have started with this relation and identified that this complex number must be Z1 and this must be Z2, because the modulus of each of these numbers is the same, the distance to the origin is the same, and if we rotate this line by 90 degrees anti-clockwise we get Z2. So these are the only two numbers that fit this first relation, and we could have worked from there.